Okay, so we are at the final headline of day one at K-First World 2022. So we're going to have a keynote address from Dr. Daescu, and it's very apt that he's going to be talking about how machines and humans can interact and learn from each other during this talk. Dr. Daescu is professor and head of the department at UT Dallas, and one thing that stood out about his work from my time at UT Dallas was that he was very focused on innovation, but grounded in reality, having real-world applicability in whatever things that he was putting out there. So without further ado, let's hear from Dr. Daescu.
Well, thank you very much, Timothy. And it is great to be the last speaker of the session, right? You get to see who stays to the end. So thank you very much to all of you for staying to the end, and thank you very much to the organizers for putting this together and for inviting me and having me as a keynote speaker. I greatly appreciate this. So we heard today about various aspects of AI and why knowledge is important and why AI systems and models have to be guided by human knowledge. And I'm going to focus in my talk on medical AI. You already heard the previous talk was about medical AI on the NLP field. This one is going to be on the imaging part of medical AI. We heard in previous talks about the problem of small data. And I'm going to illustrate here that problem of small data with two medical cases. And we will see that in one of the cases, this small term is relative. We are going to show how to turn small data into not big data, but large enough data. So we already seen AI and machine learning can be applied in almost every aspect of our lives, in almost every places, in industry, in science, medicine. Also, we can say that AI machine learning nowadays is everywhere. All right? And when we say AI machine learning, we are talking mainly about software systems. And these software systems are developed with human knowledge, right? And they are developed mostly, I will say, by humans. I mean, you might see something else here. Let's see if this pointer is working. It's not working on the screen. But I'm saying that it might be possible nowadays that we have AI systems developed by AI systems. So artificial intelligence that might develop artificial intelligence. So that's why you see this little alien head right there at the bottom. Here we are going to talk about medical imaging type of problems. And you see there in that figure a piece of human tissue, soft tissue. And you see three colors on that tissue. And those three colors correspond to three different classes. So we have necrosis or tumor necrosis, we have viable tumor, we have healthy tissue. And these classes, this heat map was generated by a machine learning model. Standard machine learning, deep learning, something like that. And we take this picture and we present it to a medical practitioner, to a medical doctor. And the medical doctor will look at the picture and say, you are telling me that's tumor and you are telling me that's necrosis, or the model is telling me that. But of course, should I trust what the model is telling me? And this is one of the main issues now in trying to put together AI machine learning with the actual practitioners. They like to look at things themselves. You feed them the result of a machine learning model, and always you'll have this question, should I double check? We are not at the point where these machine learning, artificial intelligence models that we provide are trustable from their point of view. And that thing I have encountered in my, now I will say many years of working with medical practitioners. So my focus of the past at least 8 years has been on multimodal medical data. And by multimodal here, I'm looking at the general context. So multimodal could be, for example, expression from two different types of tissues. in cancer, for example, we can have a primary site, what you see there on the right side of the image, or left if you face it like me. So you can have it a primary side, and you can have it a metastatic side, say in the lungs. Or by multimodality, we can understand images with tabular data. So we have the image, but we also have information about the patient. We also have genomic information that will become multimodal. We can have various modalities. For example, in brain cancer, we can have scans that are CT scans. We can have MRI scans of different types. We can have PET scans and so on. That will be a multimodality. Or even a multi-view image of the same thing. What you see here on the right side is various number of pictures, various pictures of a baby head. And the picture can be from the front, you see the face, or it can be from the top, or could be from the side. That we also treat as multimodality. So the first case I'm going to talk about is detection and classification of craniosynostosis, which is a deformity of the head of a newborn, a baby. If you hear the problem itself, one might say, well, it looks like a simple problem. The problems we heard about today here seem to be a lot more complex. Here's a picture, three-dimensional rendering of a newborn head. And you see it from the face, from the front, and you see it from the top. Nothing wrong with it, or maybe there is something wrong. Right? See another picture here. Is there a significant difference between the two? Now see another one here. And now here you can start to notice some significant difference, right? Naked eye, you can say, this third group here does not look quite like the first or the second. And let's look at the next one. Again, you can see something significant. So in some cases, a pediatrician can detect a case of craniosynostosis quickly just by looking at the head of the newborn. However, in many cases, they cannot. And then they have to make a decision. Should I refer this to a neurosurgeon? Neurosurgeon, they can tell because they have a lot of practice. They've seen specifically such cases, they are trying to identify them. So the first question is, do I have a problem here or not? And then if they decide they have a problem, of course, they will have to make an appointment for the patient. And there are not that many neurosurgeons, that might take months, and it's costly, and so on. And then the child can go there, the parent can go there with the baby, and they figure out there are actually no problems. They are going to be happy, but they wait, they are stressed, they pay a lot of money. So for that matter, we were approached by a neurosurgeon that told us there is a need for such automated tool, especially for those in rural areas that don't have access, rapid access or quick access to a neurosurgeon. Now, out of the 4 cases here, let's look at them. The first one is from a normal newborn baby. All the other 3 correspond to cases of craniosynostosis. So we have one case that is called metopic. And now when you look here at the picture of the baby, you kind of can see that you might have a problem. But it's still not easy to define what the problem is. You might see a bump here, right, on one side of the forehead. Next one, it's also another type of problem here we have in the third case. So I'm going to explain these 3 cases later on. So we have a metopic, unicoronal, and sagittal. So this one, again, you can see the problem, right? So when you look at the baby here, you can see, but in many cases, these features that we are going to define, they are not that clear, and they can be confusing. So what is this craniosynostosis then? It's a skull deformity, and it is caused by the premature fusion of sutures in the baby's brain. So you see here a rendering of these 4 sutures correspond to the 4 regions in the skull. And when the child is born, the skull is kind of soft, and it allows for growth. The growth is possible because these sutures are not fused together. Once they fused, the skull is not going to grow, at least along that suture. So whenever this happens in a premature way, we get one of the 3 cases. Metopic, when the one at the top of the forehead closes early, and then the head cannot expand in that direction, and then sagittal is the opposite, and unicoronal is when one of the sutures along the coronal plane closes prematurely, so fuses prematurely. And then the head will develop in only one direction. Now I'm going to pause here a little bit and say, just don't look at the head of the person in front of you. One might be tempted to do that. I remember when I seen these things first, I went back home and I looked in the mirror. I said, okay, it could have been worse. Right? So you get tempted to do such things. But seriously speaking, as a parent, when you have your baby, if you get aware of these things, then you start to be concerned. And then you would like to have a quick answer, right? You don't want, especially when there is a question mark, you don't want to wait for months to get the answer, right? You want to get the answer immediately. That's how we like to date nowadays, to get the answers, right? I have a question, I want an immediate answer. And hopefully, machine learning, artificial intelligence methods are going to help. So now let's look here at the size of the data we got from our collaborator. And we are talking here about a neurosurgeon that has been around for many years at a large medical center. And you will see immediately the problem of small data. Data set he provided to us, metopic case, 14 samples. Normal, they don't keep pictures of normal babies, so we had one sample. And then sagittal, a little bit more, and then unicoronal, 12 samples. Now, train a model to automatically give you the right answer considering the size of this data set. And a funny story here, I was working with my PhD students, and it was at a time when deep learning and CNN were like ruling the world of artificial intelligence and machine learning. Maybe they still do. And they all wanted to learn to train deep learning models and CNN models. And they were excited about getting this data, practical real data. And then when they seen the size of the data, the first reaction was, oh, we cannot train a CNN on this data. It's way too small. They lost their enthusiasm. And I said, look, there is so much more besides CNNs. We can still use this data because here is the problem, and it's a problem we want to solve. But they could get around somehow because they say, well, if we search the web, we are going to find lots of pictures of newborns, right? Seems easier said than done. Why? Well, we are talking about multimodality here, and we want the top picture and the face picture and the side picture of the same baby. You will find face pictures, right, from pictures. You will find size pictures, but who is going to take a picture of the top of a newborn? I didn't do that, and probably neither did you, right? So they could find pictures, but not from the same baby, and eventually they grew the set large enough so that they could attempt to develop a CNN model. And that's what you see here for the new data sets, right? So we have about 200 one type, 300 the other one, and so on. Especially for the normal ones, it was easy to find. So now we want two directions. One, try to extract features as directed by the neurosurgeon. What is the neurosurgeon looking for when decided what is the class? Right? We're talking about 4 classes here. And the neurosurgeon told us a lot of things, and based on that, we figure out that there are 3 features, actually, only 3 features that can make the distinction between the 4 classes. Right? So if none of the features is present, then it's normal. And then if that feature is present, it's one class. If the other one is present, the other. So these 3 features were important. We look at more than 3, but we concluded that these 3 are actually the ones that are important. So this feature, we call them the average gradient, cranial index, and the nose angle. So nose angle will be for unicoronal, the cranial index for sagittal, and the average gradient for metopic. We developed then a classic support vector machine-based machine learning model to extract, to differentiate based on these 3 features. And I'm going to show you the results immediately. And we also develop a CNN model. And we don't really understand how the decision is made, right, by the CNN model. And our training was relatively straightforward. We didn't mix features between the views because the feature were quite different, so it didn't make sense to mix them. So we trained based on the front view, we trace based on the top view. Face view will give us the nose angle. That was very important for one of the classes, while the top view will give us the other two features, right? And then we use a decision-making layer based on the support vector machine, and we predicted the class. And we got very good results. Second, we developed the CNN model. Similarly, we trained it and predicted the class, and we got good results with both of them. And you are going to see the results here. And you are going to see something very interesting. All right. So if we are looking just for one of the features, so you see one of the features at the time, we could classify quite well based on that class itself, separating the class from the other classes, using support vector machine. I mean, I was amazed considering the small size of the data set that we got such results. And when we put them all together and use the support vector machine, we got very good accuracy in training and also very good when we validated the model. Now, what happened with the CNN on the enlarged data set? The training accuracy was lower than the validation accuracy. Now, that might be possible because of the size of the data set, right? So if we are looking at the size of the data set for validation, it's quite small. So we concluded that's most likely an anomaly. And in fact, most likely the accuracy of the CNN in validation should be close to what we had in training. But we observed something even more interesting. What you see there on the right side is the heat map, the CNN activation map. So what did the CNN model use to base its conclusion, right? Where the main features were located in that activation map? And we realized that for all cases, the CNN is looking mostly at the area from the nose and eyes below. And we talked to the neurosurgeon and say, look, this is what the CNN model is telling us. This is where it's extracting most of the information to make the decision. And the neurosurgeon said, well, I never look from the eyebrows down. We always look from there up. So completely opposite direction. And here is where we talk about human knowledge and the human in the loop. Then I had a big question mark there. Is the CNN model seeing something the neurosurgeon is not seeing? Or this is just a general anomaly because the data set was not large enough? And we will go with the second choice because, frankly, the neurosurgeon also has access to CT scans that give a much better representation, and they never found any features that will go from that region down, except for the nose angle. But that's just for one case, not for all the other cases, right? But still, I mean, that question mark remains because sometimes these machine learning models might be able to observe features and things that the human eye cannot observe. Follow-up story. We say, I'm in academia, I publish papers, develop this, publish paper, and let people from industry pick up on my result and develop that result into actual applications if they want to. I mean, that's my goal. But we say, let's try it once in practice. So somehow we could find a picture of a newborn where we had the top view and the face view. And we ran our model, and we basically failed. Moreover, we went back and figured out a different data set, also from a medical facility that provided to us. In fact, from the same medical facility, but they opened up a different data set. And we ran our CNN model on that data set, and it didn't do that well. The performance degraded went somewhere down to 60% or so accuracy. However, the machine learning model, the model that was developed based on the human hand-picked features, barely degraded. So the accuracy remained almost consistent with the previous accuracy. So this knowledge first play an important role in this application. So that's one. Now the second one, here is the application we develop. It's a smartphone application, and it's actually real. It exists, it can be used. The only drawback it has is that we cannot identify the top head automatically. The top head we have to manually contour. And in fact, I challenge anyone here to develop an automating method to identify the top head. If you have that, then give it to me, and I'm going to finish this application, okay? So just that. Okay. So now the second example, again, a case of a small data set, but this time it can be made big. It's about rhabdomyosarcoma type classification and survival prediction. So rhabdomyosarcoma, it's a soft tissue sarcoma. It's actually one of the most common types of cancer in one of the most common pediatric cancer type. So in the children and the young adolescents or young adults. And we got our data again from a medical center. And what you can see there at the top is the size of the data. So again, not too large, not possible to use a CNN, at least based on what we got. There are three main types of rhabdomyosarcoma. So you see there ARMS, ERMS, and SCRMS, and I'm not going to explain this, I will take time. But for a trained pathologist, most of the time, it's not too difficult to differentiate. However, in some cases, it is very difficult, to the point that they cannot tell just based on the medical image. So we did the same thing. We extended the data set. We made it larger. And in this case, we could do that because of the properties of the original data set. The original data set comes as a digital image, which is called a whole slide image, which is very big. And because in this case we know we have cancer, we only want to identify the subtype, we could look at small portions of the image and try to identify the subtype. So basically all methods apply to such imaging. They will extract small tiles from the big image. So you start with, say, one image, you extract 1,000 tiles from it, then you go to the next image, you extract another 1,000 tiles, so you get to a larger data set. And you infer your result from the larger data set. Right? So we had a small data problem. However, this was not a real problem in this case because we can actually make it a large enough data. And we trained our models and we did very well. And we did very well this time, and better actually, with deep learning models. We had enough data to train, and they perform well. And they perform well in various validations. So that was actually good to hear. But here is the reality for medical data sets that are publicly available. They are small, and the trick we played in the second case can rarely be used. So what you see here, 5 most common types of cancer, right? Breast cancer, we look for public data sets that we could use, about 400 images, and we have 4 classes. Prostate, about 1,000 images, we have 4 classes. The data sets are small. So for that matter, the decision making has to follow human knowledge, has to follow human rules, and has to extract human-defined features. That's what we see here actually for most data sets that we look at. So most data sets are small. Deep learning methods are very popular. However, in order to apply them on these data sets, we need to grow the data set, right? And there are standard methods, right, to do data augmentation. You can rotate, you can flip, you can have small alterations. However, in many cases, such data augmentation processes might create problems. And whenever you use these data sets, you have to pay attention on how the data set was augmented. Do you have the original or do you have an augmenting data set? And I'm going to give you an example. Data set, you can find it online, it starts with 500 images per class, not enough to train a CNN. And then these 500 images are augmented to create about 20-something thousand images per class. Now you can train a CNN model. But then I seen these publications with 99% accuracy. And I love that result. It's just that some of them improve over my results that had just 90% accuracy and on which I worked for years to get 90%. And then I see these results with 99% and I say, what's wrong with them? And I was thinking, if I go to the medical doctors I'm working with, and I show them, oh, look, these machine learning models, they give you 99% accuracy, they will say, what's wrong with you? You really believe that accuracy? I cannot believe it. Huh? And yes, sometimes there are problems. Why is that? Because it is possible that some of the models used on this enhanced data set, on this augmented data set, they are invariant to transformations. And I'm giving here the example of topological data analysis. Topological data analysis has penetrated recently, and it's a very powerful, interpretable, explainable method. It is invariant to transformations. You take an image, you rotate, you flip, and so on, you get the same answer. So if you use that, and you go from 500 and you go 25,000, then you are going to overfit your data. So yes, you are going to get 100% accuracy, but that's not real accuracy. And we've seen that in at least one case. Right? So that's one thing here. And then when we are looking at data augmentation for deep learning models, it comes down to the following thing. I have not seen a theory addressing the impact of data augmentation on deep learning models, a general theory. And without such a theory, how much trust can we put in the outcome of those models? And maybe that's the reason why they fail when you move from one data set to another data set, like it happened in our case. That's a possibility. So going down from here, I will conclude by saying that we need a human in the loop. We need to start with the human knowledge, and to some extent, we need to return to proofs and guarantees. And I call these things theorems. So I'm not talking about that theorems that you learn about in math, but something close to it. Give me a guarantee of performance, something that I can understand, something that I can explain. Here is an example of topological data analysis. This picture you can understand, this picture you can explain. You can see the three classes and you can see that the curves are different, right? Green class, curve is looking different from the blue class or from the orange class. Topological data analysis is very powerful because it can be interpreted, it can be explained. We tried it on some of our past models on the same data that's publicly available, and you see here three results. Three previous results. Two are mine from my group, and one is more recent from a different group. So first one is based on support vector machines, about 90% accuracy, but quite stable. If you move it from dataset quite stable. Second one, based on CNNs, spend a lot of time, lots of training time, 93%. Last one I've seen was about 94%. TDA model, very fast, explainable, interpretable, more than 94%. Proved to be the best. That seems to be the right direction to go. And with this, I'm going to conclude and open it up for questions. But I would like to thank all my collaborators. And what you see here in the list are my collaborators on only these two projects that I talk about here. I have a few more, and you will see that they come from all places. So collaborators from Google, Microsoft, Verizon, my PhD students, medical oncologists, pathologists, neurosurgeons, and mathematicians. Mathematician, we didn't use the mathematician for theorem proving, but he proved to be really useful. Thank you very much.
Thank you, Dr. Daescu, for a very insightful talk on medical images and small data. So let's open up the floor for any questions if you have one.
Yeah, thank you, sir. I would like to ask, because you mentioned about the public data sets, right?
Yes.
So when I do with dosing, the hardest part is the unbalancing data. So how can you overcome dosing with augmented data?
We are looking to find more data, if possible at all, like we did in, say, craniosynostosis case, or otherwise, we augment if it needs to be augmented, if we want to use things like CNN. But to the extent possible, we try to add data. That's the safest way to handle it. Like, again, craniosynostosis, normal case, we have one sample from the medical center, but then we could find hundreds of samples online.
Because some of the medical diagnosis, they facing with the rare data. So just a few data and we cannot find out all the data. So how can we?
So what I was saying in that case, we do not have the right answer or we cannot trust the answer. So the models are not trustable. And that's one point that I'm making. So again, we have to make a distinction here. We do an experiment and we get good results and we can even publish a paper. But can that be moved to actual clinical practice? The answer is no, especially when we have a case when the data set is small. What I showed for rhabdomyosarcoma, that was for large data sets now because we could generate those. That's the type of models that I will trust and say, okay, this I can trust to move it to a clinical practice. If, of course, the medical doctors will trust me on doing that. I mean, it's a different story. But we showcase it in different places and it worked very well. So, but in other cases, I will say no, the data is too small, definitely needs a lot more work. And we have to recognize that. And we have to be the ones that say, we stop here, we don't push it, and we don't proceed.
Thank you, Professor. And I have a question because I'm curious about the structure of the CNN you use and then how you can separate the data and how the cross validation you apply to achieve this kind of level of accuracy. Because on my own, I also apply the same for my. In one of my paper, I cut the piece of paper, I cut the piece of the image to generate the data. You different contrast in contrastive learning, but Kaiaply just received some kind of more than just 91 or 92% of accuracy. So I'm curious, you can achieve.
So which of the two problems are you asking about?
I'm curious about the structure of the network you train.
For which of the problems? For the craniosynostosis, for the rhabdomyosarcoma?
The last line, in the last line.
Rhabdomyosarcoma.
Yeah.
So we develop our own network. So we just train it from scratch. So we have our own architecture for that. So we didn't use pre-train and so on. We had experience before with pre-train, and they never work as good as the ones that we develop ourselves. So think about it. Those pre-trained networks, they are pre-trained on human faces. And now here we apply them to identify nuclei in images and count them, and not the same thing. So they didn't, those pre-trained networks didn't seem to have that much. I mean, they will give you good results, but they will not give you the best results. And details are in the papers, so you can just go and take a look there or send me an email and I'll give you a reference to the papers and you will see what we did and how we did it.
In the first project, you mentioned the machine learning model that looked eyes down turned out to be incorrect.
That was the CNN model, right? And I mean, I would not say 100% was incorrect. It just seems unlikely to capture the right features. That's what I'm saying here.
Right.
Capture the right feature. So the accuracy was quite good. Right?
Have you seen circumstances where, say, that the data-driven machine learning model captured new features that that humans weren't aware of, and actually increase the accuracy overall of both the human rules and the...
That's a great question, and the answer is yes. And well, I know how much I should maybe say about it, but yes, we were working with some pathologists at a government agency, so it's a very, very reputed place, and the pathology was well-trained and so on. And the pathologist was very accurate in delineating the classes. Okay, so this is viable tumor, this is necrosis, this is normal tissue. And I want the machine learning model to be as precise as I am. So pathologists spend a lot of time making sure that gets the right thing. And we ran the machine learning models and they work very nicely, except for some little thing somewhere in the middle of the tumor that were different from the pathologist assessment. And they will look like white spots. And the pathologist will classify them as tumor, and the machine learning model will classify them as something else, put in class normal, because it was not necrosis, it was not viable tumor. And then we had these slight differences. Is it 35% viable tumor, or is it 35.2% viable tumor? And eventually, the pathologist went back and started to look more carefully at those images and started to read more about the possibility of white spots within tumor mass. And it found out that indeed that is a phenomenon and those white spots corresponded to some type of fat tissue that may arise within the tumor. So that was kind of like a vindication for the machine learning model, because it just did not get fooled. Right? So it would have been easy for us if something is abnormal and is small and is within the tumor mass, just write it out as tumor. Because that one we can infer quickly. Right? It's something inside in the middle, who cares? But we didn't want to do that. Right? We let the machine model make the decision, and although at the beginning it was ruled as not being correct, later on it was found out that the decision was correct. So that's a question that I discussed multiple times with medical practitioners, saying, here is what the model tells you, here is what you tell me. How confident are you that your answer is the right one? Because sometimes there might be clues that you don't observe. And that's why I say for the first case, when those features are extracted from the eye nose area, that I don't discount that case 100%. Because maybe the model may identify something that we cannot see with the naked eye. We don't realize it's there. Nose curvature is there, and we know it's a distinguishing factor for one of the classes. Maybe there is something else with the eyes, with the eyebrows, with the cheeks, that will correspond to the other classes. We don't know. But what we know was that when we took the model to a new data set that actually had better imaging because they were higher fidelity, higher definition images, it didn't do well. The machine learning didn't do well. That we know. While the other one, the CNN model did not do well. While the machine learning model, the ones that was trained on human feature, it maintained the performance. Thank you very much. Appreciate it. Have a good evening and have a great dinner.
Thank you, Dr. Daescu. Great way to finish the session and day one at K-First World. That started off with a bang with Dr. Christopher Wen's talk. And we had a lot of great talks in between as well.